Hi, everybody. I am Dave from Librato, and I bet you're probably wondering, Dave, what is the world's foremost authority on writing technical nonfiction books that have squiggly things on the cover doing here at Monitorama, talking about signal processing? And I think that's a really great and valid question, and I can already see that you are an insightful and intelligent audience. The TLDR is that monitoring is a signal processing problem. And in our context, that sort of makes it a stream processing problem. And I can hear you saying, Dave, that sounds really thought leadery, and I'm therefore kind of skeptical of both your point and your humanity. Which, fair enough, let me try to explain what I mean by that by giving you an example that I hope we're all more or less familiar with, which is live music, which is also a real-time signal processing problem. So likely data sources include like a handful of microphones, like the one that I'm hopefully speaking into now, and also a guitar and a bass, a bass. And you might think that these are instruments, but they're not. They're actually sensors that detect vibration. So in the case of the guitars, you have these things under the strings called pickups. They're basically like magnets with wire coiled around them. And the strings themselves are made of like nickel and steel. So when you strum them, the movement of the vibration in that magnetic field in which those strings are immersed basically pushes and pulls electrons in that coil. And the microphone that I'm speaking into right now also has a wire coil in it next to a magnet, but this one is actually attached to a really thin piece of material called a diaphragm. And that diaphragm is so thin that the air pressure differentials caused by the sheer force of my thought leadering is causing it to wobble back and forth. And therefore, that wire coil is also wobbling back and forth in that magnetic field. It's forcing electrons to move inside the coil. And the coil is attached to a wire, and the wire is attached to whatever it's attached to down here somewhere. And all of the electrons in all of that material, they're tied together like train cars. So when those strings vibrate in one direction, all of those electrons all the way down that wire get pushed. And when the string vibrates back the other direction, all of those electrons get pulled back, right? Sorry. So the strings wobble back and forth like 400,000 times per second. So what you end up with is like this real-time of signals coming from several different types of sensor from these various sources, right? And if you're in a garage band, each of these signals gets sent to its own destination. So we treat them as disparate, and then we persist them in a disparate way, right? Sound familiar? We collect, we persist all of these disparate signals separately. Metaphor, meet audience. So sometimes we visualize these, right? Sometimes we alert on them. And when we get serious, like when we outgrow the garage, we start using this thing called a mixer, and we send all of the signals into a mixer instead. And mixers are pretty great. They're basically a big square series of dials that we can use to perform like these arbitrary signal processing tasks on our input signals. Like mixers can translate inbound signals of various types into a standardized normal type, right? Mixers have things like low pass filters and preamps built in. So if I'm getting like a noisy signal, the mixer can like take care of that noise automatically, right, by filtering some of it out. And of course, the mixer actually gets its name from its ability to multiplex signals. So I can aggregate a bunch of related signals from different sources together into like one signal and then persist it as a single stream, right? And then maybe most importantly, or maybe, best of all, the mixer has this effects channel built in, or if it's a good mixer, lots of effects channels. And these are really awesome. They give us the ability to basically take a copy of our signal and send it to a bunch of external stream processors and then re-ingest the result from those stream processors in real time. And now you're thinking, okay, Dave, your adorable yet tenuous audio processing analogy is starting to break down here because there is nothing analogous to effects channels in the monitoring world. Or is there? So, we've been here for days now, it feels like we've been here for days now, talking about these anomaly detection systems that Twitter and Netflix are working on. So these guys are out there thinking about these sort of data science models for how to detect anomalies in multivariate time series. And to be fair, we've been doing this for a long time. Like we've been looking forever, it seems like, for this sort of general purpose exponential smoothing based algorithm that's going to detect anomalies in all of our time series data and save us from having to watch the cost. You're with me, right? But Tufik is up here telling us our data isn't Gaussian, and Coda and Abe and Dr. Neil and Theo and all these smart people are up here telling us for years our metrics data is not normally distributed yet. It's exponential smoothing is not going to work. So I think we're finally over this phase. I think most of us have come with the effect, right? That no amount of mu sigma and extra super fancy hybridized exponential smoothing is going to give us a generalized model for anomaly detection, probably, right? Me just having said that probably sprung one into being. But the point is that we're starting to look at a bunch of different models that are more or less optimized for specific types of metric data, and that's a good thing because now we're also working with actual data scientists. And data scientists are also great. They have all of these crazy tools they can use to categorize stuff and detect patterns of data. They can take some extreme scrutinized D tests and sprinkle chicken fried linear regression modeling on that. They have a lot of tools. But the problem is that data scientists use data science tools, right? R and SciPy and NumPy, and engineers use engineer tools like Java and Golang and the JVM stuff. Java. I was what word did I say? It's funny. Yeah, so basically you have to bridge this gap. You have to map the model to the infrastructure, right? So you need this data engineer, which is a platypus animal. It's neither engineer nor scientist. It's sort of between the two to actually instantiate this model, map the model to the infrastructure. And I think what we're finding out is that this is actually really hard to do. It's making a model is actually just the beginning of the problem. We're actually going to have to use the model, right? Case in point, Twitter puts this amazing model on GitHub. This thing is probably as close as we've ever been to a magic formula that detects, anomaly detection in multivariate time series. So, Twitter won the math. Let's all go home, right? We're done here. But the problem is that none of us literally are architected today to use this model. Twitter isn't even architected to use this model. And now you're thinking, how do you know, Dave? You're not smart enough to work with Twitter, which, fair point, I'm not. So let Twitter speak.
Here are a few other lessons. So, one of the things is the model is actually in R, and all of our infrastructure is on the JVM. So for a while we were how are you going to kind of get around this? And there's really no good implementation of this model in Java or Scala. So we tried a couple of these JVM R bridges. You might see things like JVM-R, Rengen, RJava, and each one had its kind of own set of issues. So, either they had high latency, so if we're trying to do minutely anomaly detection, it just wouldn't run fast enough. And the other thing is that a lot of these didn't have great exception handling. So if something went wrong and, applying the model, it wasn't really clear sort of, okay, what's actually going on here.
So yeah, I feel that guy's pain, right? So this engineer has built his, he's Twitter, man. He's built a fantastic bespoke monitoring system of his dreams. He has more money than, I'll ever have, certainly. And along comes this magical anomaly detection protocol, except it sort of depends on these stream decomposition algorithms that are literally not implemented anywhere but R, because this is probably part of someone's PhD dissertation, and that's where they implemented it. And porting it means go find the paper and re-implement this in Java. And nobody can tell you if you got this right, whoever wrote the paper. And even they, if you can find them, if they aren't already working for the NSA, will be I don't speak Java, I don't know. So what do you do with this? What does Twitter engineering do? It's an amazing model. You can't not use this. It's amazing, right? So they batch process native R as a Mesos job. And now you're thinking, Dave, that's silly. Who would batch process native R as a Mesos job? But who are we to judge? At least that's an answer, because we're over here with Nagios extracting 10-minute resolution metrics with a Python script and piping to a JavaScript program that's piping to a Python script. So what are we going to do with this R thing is actually the question, right? Does R even work with standard in? Does anybody know? I'm sorry, what's that you're thinking? It sure would be nice if we had this big square series of dials that we could use to perform arbitrary processing in our input signals, one that lets us isolate and tee off individual signals in real time to any number of external signal transformation processes and then like re-ingest the result. I agree with you. I think that would be a fantastic idea. But wait, what about our tenuously glued together string of open source tools? Like I have commits on these tools. I've written books about some of these tools. Like I'm committed to this like tool chain. So you know what we could do is we could rip out StatSD and replace it with some Hecker or Riemann. And then we could bolt the R thing onto that and sprinkle some HA on it and add some relays and caching to scale it. Dude, we could write a Monitorama CFD about this. Okay. Okay, Dave, you're thinking your sort of like sarcastic, passive-aggressive, scorn-filled rant has convinced me. Let us assume for a moment that monitoring is actually a stream processing problem. How do telemetry systems that employ proper stream processing infrastructure even work? Well, I'm glad you asked. This one that we're looking at now is the one that we actually use inside Librato. It's based on Apache Storm. And just to put it in context, it sits sort of like right here in the middle of our infrastructure. So now you're thinking, wow, Dave, if I squint at it, I can almost see, it looks like a big square series of dots. Arbitrary signal processing, right? Wow, right again. I mean, you guys, guys and gals, excuse me, are blowing it out of the, you know, park, whatever the sports analogy is, for doing well. Your insight is bordering on clairvoyance at this point. So. Anyway, these big blue squares in the center are topologies, which is Storm vernacular for networks of hosts that work together to solve a given problem. In fact, confusing vernacular may be Storm's crowning achievement. Inside a topology are machines that run spouts and bolts, which are these code primitives provided by the Storm libraries. So your job is basically to implement as code spouts that read and process incoming data from things, and the bolts which accept processed data and then sort of export the result to external things, right? And the nice thing about Storm is that it sort of configures everything for you once you put this stuff in Zookeeper. So you basically tell your machines to register with Zookeeper, you throw your spouts and bolts in there as code primitives, and Storm pretty much takes care of all the runtime details of like instantiating all of these spouts and bolts across the hardware as threads, given some pointers by you. So when you add new systems, you can generally just tell them, hey, go register with Zookeeper, and they'll just start taking traffic. It is kind of magical. It works very well. So spouts and bolts are basically like pollers and emitters, right? We argue a lot about push versus pull in monitoring. In stream processing, you do both. Caveat, before I get into the actual arrows pointing at boxes stuff in earnest, the caveat is to avoid letting your topologies write directly to each other. So this is something the gentleman from Google brought up. You run into these problems where you have a latency in one service that can basically backflow up any other services and eventually wind up taking everything down. So in all the diagrams I'm going to be showing you in a moment, there are definitely like topologies pointing at each other with arrows. But in reality, what's happening is we always isolate the latency of our transformation processing from our storage by inserting a queue between it, right? So each topology in real life consists of at least one spout that reads from a queue or topic and Kafka's, and at least one bolt that writes to a different topic. So they basically like leave messages for each other. And that keeps things sort of like asynchronous and protects us from like short-lived performance problems. And now you're thinking, Dave, I bet isolating your storage latency from your transformation processing latency also makes it easier to find out where the bottlenecks are. And you'd be right again. Not the best audience ever. So anyway, at Librato, all our stream processing starts with our SSA topology, which is sort of this general purpose ingress processor. SSA, as you've already guessed, stands for server-side aggregation. Its primary job is to aggregate inbound metrics. So it's a really common use case for us that we have a customer who's paying for like 60-second resolution, but they're actually sending like 5-second samples. That's not a problem. SSA basically catches all those measurements and emits basically a summary data point of all of those measurements at the resolution that the customer is actually paying for. And this pattern that you're looking at right here, by the way, is actually how we perform all of our time series summarization. So all summarization happens in stream processing between ingest and persist. There's no built-in, summarization functionality in the persistence layer. So SSA feeds both a 60-second roll-up topology as well as a topology that writes raw resolution metrics straight into the persistence layer. So yes, you can have several bolts per topology that basically write to different places, and parenthetically you can have different spouts in the same topology that read from multiple places. Then that 60-second topology feeds a 900, the 900 feeds a 3600, and so on and so on. Each of these sort of holds and aggregates measurements in memory for a given amount of time, just like we've already said, and then just emits the summarized result back into the persistence layer. And now you're thinking, Dave, this solves a ton of problems that the monitoring community has traditionally struggled with respect to storage and summarization. Wow, you know, I think you guys might be right. Because every piece of this architecture scales. Like, it's distributed by definition. We can throw hardware at this without having to configure anything. And it completely isolates our transformation processing from our storage, by which I mean we're no longer constrained to a specific data storage format by virtue of the type of database that we're using. We're not constrained to a particular summarization function per metric. We can do things differently for different metrics in this string processing tier. And if we want to experiment with different storage backends, if we want to experiment with different ingest, if we want to experiment with different schema, we can basically spin up other topologies that run in parallel to these, and just run it all in parallel. All you need is more boxes. So you're thinking to yourself, Dave, that's a lot of boxes. It sounds really complicated, and I'm not sure that I want to learn how it all works. But that's okay, because we're actually just running like 8 instances in our ingestion pipeline. So we're literally running ingestion pipeline for a public-facing multi-tenant telemetry system on 8 VMs, which I think is a pretty good story. I mean, this usually runs between 40 and 60 worker threads, processes on the order of hundreds of thousands of tuples per second. SSA actually does a lot more ingestion transformation processing than I have time to talk about right now. But I will mention that Mike Hefner, who looks like this, is on our, is on site here, and this is the my head of data engineering. So I encourage you to find him and bombard him with all of your overly pedantic complaints about all of the stuff you think I just technically misrepresented. Anyway, SSA feeds a whole slew of other topologies that I haven't mentioned. One that I have time to talk about is our alerting topology. So alerting is another thing that we're actually doing in the stream processing tier. So this isn't like you select a metric, you persist it, and then you go to analyze, right, and alert on it. We're actually doing alerting as a stream processing topology. And I'll bring this diagram up to draw your attention sort of to the RDS instance up there at the top. There you go, I think that's RDS. We use that database basically to cache information from other services. So in this example, in the context of alerting, for each measurement that SSA topology reads off of its topic, it's going to have to go to an SQL memcache or an SQL back to memcached and say, hey, is there an alert configured for this metric? And if there is, it will bundle up a copy of the measurement along with some metadata and then send a copy of the whole sort of blob to the alerting topology. And what the alerting topology does with that actually depends on the details of the alert criteria that was crafted by the user. So the alerting topology also has to go to that memcached and sort of ask for details on the alert. Like, is this a simple threshold? Because then we can, just sort of compare thresholds in alert. Or is it like a sliding window alert? And if it is, the topology will already sort of have this in-memory queue of the measurements sort of in a similar way that the roll-up topologies do, and you can do its processing that way. So if we detect a problem or the clearing of a problem, a bolt in that alerting topology bundles up that info, alerts a mess or emits a message, into the alert processing service. And this is a sort of a traditional services-based, service which figures out what to do about it, who to send it to, and how, whom, I guess, to send it to, and how. So if you ask them, my data engineering team will tell you that Storm is pretty okay. It's a direct quote. It works, it scales, it basically abstracts away annoying things like interacting with threads and implementing them and queues. It makes decent delivery guarantees. Some of that is actually on you. But all that said, Storm doesn't give you a lot of insight into how it's doing what it's doing. So the contract is basically, here are some primitives, you implement them, and we'll take it from here. And if stuff starts to get slow, basically throw some more hardware at it, and try not to worry too much about how it's using what you just threw at it. Because, so for example, here's like a CPU graph of our SSH topology, and you can see it runs around like 40% pretty standard. And we're Librato, I mean, for crying out loud. We instrument our topologies like, we have a pretty good visibility in like how these things work. We know that they're not working this hard, or they shouldn't be. But we really can't sort of like isolate this resource utilization. We can't figure out where the CPU overhead is being spent inside of Storm. So I think it's fair to say that we'd like some better visibility. I think we'd like some more granular provisioning control. We'd like an architecture that's just generally a little easier to reason about. And so we're starting to evaluate a few other options. Actually, we started earlier this year evaluating some options. In the last few days, we brought up sort of this experimental purpose-built stream processing service we're calling Super Chief. I like it a lot. That's like, I don't usually like the names that we call our services. If you see me talk before, I'm like, it's called Bubbles. This is pretty cool, Super Chief, Super Chief. I like it. Anyway, so you're thinking probably now that it actually probably sounds, doesn't it sound dangerous, Dave, to like bring up a parallel experimental processing service in your hot hat? No, actually it's pretty darn safe. Like I mentioned before, if you have a proper stream processing tier, this is definitely one of the things that you have it there for, so that you can bring up parallel ingest pipeline and run it in parallel to see how it would work. And in this case, our initial experiments seem to indicate that Super Chief is about on the order of a magnitude more efficient. So we can really comfortably run a production workload on 2 instances compared to like the 8 that we're running now with Storm. And I think that's pretty close to all I have time for. So I'm just going to back away from the podium. If you have questions, comments, points of clarification, feel free. I will attempt to answer them.
We looked at Heron?
No, I don't think we have looked at Heron. You guys can yell at me, I don't know where you are, but I've been sitting in their meetings, basically, is like the extent of my experience. So I don't think that we have, but it wouldn't surprise me, right? Like literally, I just found out about Super Chief yesterday. Like we were all at lunch, and I'm like giving this data streaming talk, and the CTO, Joe, like, looks over at me and he's like, have you heard of Super Chief? I'm like, what? Literally. So it was like yesterday. So all this, yeah, never mind. It's fine. Can I drop this mic?